Without further ado, I shall pass you over to Dr. Charlotte Simmonds, who has joined us from the Cavalier Institute for Cosmology, and who will be talking about unveiling the mysteries of the universe.
Yeah. Hello. Can you hear me? The mic on? Yeah. Okay. So thank you, Jacob. I am Charlotte, as my slides say, and I work in the Cavalier and the Cavendish, and also I am part of JWST. You have probably never heard about JWST before. This is one of the teams that actually built JWST, which is a telescope that I'm going to tell you about today. So I work with the people that worked for 30 years building this amazing telescope, and we have access to the most amazing data to date that we have ever had of the universe. So you're going to see some cool stuff today. And I want to start this talk by doing something a little bit unorthodox, and I'm going to ask you to take your phones out and go to that link. Okay, all the phones are out. Thank you very much. There's a QR and there's a link if you're old like me and you don't know how to do QR. This is an interactive viewer from the JWST collaboration that we made just so that we don't just keep our data, but we can share it with everyone who is interested in the universe. So if you go here, you will find a viewer that will look a bit like this. If you want instructions on how to use it, we have a YouTube channel that is up there. That's Kevin Hainline, and he will teach you how to use it and how to look at the different wavelengths that we have access to. And this doesn't look like much, right? It just looks like a big thumbnail. However, if you zoom in, you'll start to see all sorts of amazing stuff. This is groundbreaking. Before 2 years ago, we didn't have anything like this. So if you're interested in astronomy, or if you're having a bad day, sometimes it's nice to just look at this for a bit and remember how big and beautiful the universe is. Makes you feel a bit better once in a while. So I would encourage you to go there. And even if you're bored, I once went looking for cats. I didn't find any cats, but I found a snail. So if you find a cat, let me know. So now we can go to the normal talk. So today there's 3 steps to this talk. First, I will tell you a bit about JWST. Second, I will show you a bit about how the nearby universe looks with JWST and what we can learn from that. And then we will go a bit to what we have learned about the early universe in these past almost 2 years that JWST has been producing science. So, what is JWST? It is a James Webb Space Telescope. It was launched in Christmas 2021. This is how it looked like while it was being built. So see, it's quite huge. These are people for scale. These are real people. The primary mirror is 6.5 meters across, and it's composed of 18 little mirrors. And the way that it was sent to space was like this, all scrunched up. The reason for that is that it had to be launched into space inside of a rocket. And for it to fit inside of a rocket, it has to be folded up. There's no other way. So that also puts a constraint on how big we can make it. It was supposed to last for 10 years, but now it went so perfectly in the launch and everything that happened that we think we'll have science for at least 20 years, which is quite amazing. So here we have an animation. When it went to space, it went all scrunched up, as I said. The first thing to unfold were the sun shields, which are these gray things. They're about a tennis court size in size. And then the primary mirror unfolded for it to become the JWST that we know and love today. So there's 2 main questions you could have at this point. I'm sorry, I'm going to take this off. So there's 2 main questions you could have. One is, why do we need such big telescopes? Because we keep spending money on them. So why do we keep making bigger and bigger telescopes? And then why do we have to send them to space? We have a perfectly good Earth here. Why don't we do it? So the first I'm going to answer is, why so big? And the reason there's an eye there, it's because telescopes work in a very similar way that our eyes work, our pupil. If you enter a dark room, your pupil will enlarge so that you can capture more light and see better. So the bigger your capturing area is of light, the better you will see and the farther you will see. So that's why we're always going for bigger. Now, the thing about sending it to space is that we can't have an infinitely big telescope, so there's a limit. But if we could, we would have a huge, huge telescope in space. Now, why do we do it in space? You might be wondering what that is. I'll get to it. There's two reasons. One is that the Earth's atmosphere is a problem in general when observing. We do have loads of telescopes in my home country, in Chile, but the atmosphere is always a problem. It absorbs the UV light. It also has turbulence. So ideally, things would be in space. On the moon, maybe, would be great. But in JWST's case, it's more than that. JWST is an infrared telescope. It doesn't look in visible light, but it looks in infrared. Have you ever seen a thermal image of something? Yeah? These are just a couple of people, and they shine so bright in the thermal, right? If JWST was on Earth, it would go insane because everything with a temperature emits in the infrared. So it needs to be isolated, it needs to be in space, it needs to be cold, it needs to be away from us so that we don't shine on it. So that's why we need it in space. And now there might be a third question coming up. Why did we give it infrared eyes and not other wavelengths of eyes? So to show this, oh yeah, by the way, there's loads of cats in my talk, so get used to it. Humans and creatures like humans observe in the visible wavelength of light. So as you may know, light can be decomposed into different colors, the colors of the rainbow. And the violet is the shortest of wavelengths, but as you go to the redder colors, the wavelength of the light gets longer and longer. Now this is just a tiny bit of the universe that we're seeing, because the visible light is only this tiny bit of the entire electromagnetic spectrum. So we're missing out on all the very energetic stuff, but we're also missing out on all the red that we cannot see with our eyes, but we need instruments for. So JWST is here in the infrared, a bit redder than what we can actually see. And that makes it perfect for its purpose, which was to look further and deeper than ever before. What it was built for was to look deeper into the universe and see the earliest galaxies, maybe even see the first stars that ever formed. And so why that works for us is due to an effect called redshift. So as you see here, this brilliant animation, as the universe expands, everything gets away from everything. All the galaxies get further away from every other galaxy. That not only makes things be more far away, but the light that we see from them also gets stretched. And so something that was originally here in the visible light, the visible cat, if you take the same galaxy and put it very far away, the same galaxy will not look blue anymore, it will look red. Even though it's the same galaxy, it's just far away because the light is being stretched. So that means that with JWST, we can look at things that are far away as if they were close by, because we're seeing their optical features, but in galaxies that are very, very, very far away in the early universe. So just as a little summary about why. So JWST can unveil mysteries in the optical if we see it close by. For example, here, this is tiny. This is an infrared camera. And you can come play with it later if you want. If you are very close by to something, you will see things that are hidden. I could hide my hands behind a bag, just like this man. Who knows what he's doing with his hands? We don't see them. We don't know how many fingers are up. But if we look at him with an infrared camera, we can see right through the bag. So in galaxies that are close by, we will see details that we can't see with the visible light. But in galaxies that are more far away, we get to see this visible part, but just stretched into the infrared. So it gives us, both close and far away, a new view of the universe that we never had before, not in this detail. As a comparison, you might be familiar with Hubble telescope. So this is HST. This is what we had before JWST, although we still have it. Hubble still works, and it's great. Now, Hubble had a smaller mirror. This is it for comparison, compared to JWST. So it can collect less light. But not only that, Hubble also observed in a different wavelength. So it observed in visible and UV, which is a bit bluer. So it means that it couldn't go as far as JWST could. So Hubble could observe where the modern galaxies formed, which is still pretty far away, but JWST can potentially observe up to the point when the first stars in the universe were formed. And this is the first deep field image of JWST compared to what Hubble could see. So Hubble, JWST, Hubble, JWST. And you'll see in the Hubble there's a lot of features missing that we do see with JWST. You'll notice that in the JWST image, there's lots of these red dots that appear. These are not fake. These are just galaxies that are really, really far away and redshifted that we could not see before. So it's pretty amazing. I hope I convinced you about how amazing it is, and to go and find your own galaxies later. So if we look at the nearby galaxies in our neighborhood, what can we see? I'll just show you a couple of my favorite images and what we can learn from them. So this here is a nebula that is in our own galaxy. You might have known it as Pillars of Creation. It looks like a giant, scary hand as well, whatever you prefer. And this is a stellar nursery. This means that this is where stars are being born in nebulas. So just a quick course on how stars are formed. You need cold molecular gas. So it needs to be cold enough that it can collapse under its own gravity, and then stars are formed. And this is what you see here. This is optical images. So you can't really see through it. You just see like a very dusty thing. And this looks maybe blurry. I don't know, how many stars do you see? Maybe 100, if you're generous? Now, remember the man with the bag. So what happens when we turn on JWST instead? What do we see? Lots of stars, you know? It's so beautiful. And here we can see a bit more through where the dust was. And these tips here that are very red, images in astronomy tend to be color-coded by temperature, is a good way to say it. So bluer is warmer and redder is colder. And these tips are very cold gas. It's exactly where stars are being born. So that's pretty cool, I think. The next one, and this is my absolute favorite, this is called the Phantom Galaxy. It's just a fancy name for a galaxy that's actually Messier 74. It looks like a spiral galaxy. It looks like what you would expect from the Milky Way, or what we've seen in Andromeda, maybe, any other spiral that you know. So this is Hubble and optical. And it looks pretty perfect. There's no disruptance. It's just a spiral, right? What do you think happens if we turn on JWST? Any clue? It's full of holes. So JWST can see through the dust and see the dust structure in the galaxy, and what looks like a perfect little galaxy actually is full of holes. And actually it gives me a little bit of comfort as a human. Galaxies are a bit like us. They can sometimes look really happy, but hey, you have to look beneath the surface. So all these holes here, if you're wondering, are what's left behind when massive stars die as supernovae. So they explode and they blow off all the dust, and they leave all these holes here that we can't just see in the optical. And the Phantom Galaxy isn't special. It was, I think, the first one that we looked at it like this. But recently in the FANGS program, these are 19 galaxies that are nearby, all spirals, face on, which means that they're looking at us like this. And they all have a similar structure. So nearby, it's quite amazing what we can see and what we can learn about how galaxies work with JWST. Now, going to the early universe. This is good. I think I ran through it because I thought I would not have time. So I'll go a bit through the generals, and then I will share a bit of what I actually do in the day-to-day, what my papers are about, in case you're interested. So one of the first things that surprised astronomers was that when they started looking at this very distant universe, the expectation was that galaxies would be small, maybe not much interactions, definitely no spirals or anything like that, because all these structures, to our knowledge, take a lot of time for galaxies to settle, and then they start showing these structures. But when they're young, you don't really see that, or we thought we didn't see that. And then we used JWST, and since it's the first time we are actually observing this far, it turns out that our models didn't exactly predict what we actually saw. And we found, this is from the Sears collaboration, which also works with JWST. There's actually quite a big diversity of shapes in galaxies in the very early universe. So this is 0.5 to 2 billion years after the Big Bang. That is very early universe. So we're still figuring it out, but it's one of the exciting things about science. You find something you didn't expect, so you just go into the rabbit hole and keep finding new ways to explain things. So this has been quite amazing. On the other hand, on the jade side, we also found very early galaxies. And the reason I'm showing this one is that this has been the scandal, or it was a bit for a while. It was scandalous in my community, at least. So this is how it looks like in images. But JWST has imaging on one side, but also has spectra, which allows you to observe the spectrum of the galaxy, which is a chemical fingerprint. So it tells you which elements it has and which abundance, how it looks exactly. It's just like our fingerprints. It tells you it's unique to a galaxy. And they turned this on for GNZ11. That's a beautiful name. And it looks something like this, which actually, I know it doesn't mean much, just looking at it. But we had never had access to a data like this, so far away. And what made it so controversial is that I think in 1 week, at least 4 papers came out about the same galaxy, all saying something different. So some people said it's a supermassive black hole. This is clear. This is obvious, because we have the chemical fingerprint. But then other people, no, this is clearly just a normal galaxy. It's just forming stars. And I don't know, in astronomy, that's a pretty big debate. Maybe we're not as exciting as other fields, but but it was quite a scandal. And people are still not sure what this is, but we're on it. So what I do is I work on something called Epoch of Reionisation. So the universe, after the Big Bang, was really hot. It was hot soup. I'm sure you've heard that before. Hot soup, no atoms can be formed, basically, because all the protons and electrons, it's all messed up. It's too hot for anything to actually get together. But after a while, as it expanded, it started to cool down and gave rise to what we call, this is a very cool name, the Dark Ages. So it's called the Dark Ages because it was just a neutral universe. There were no stars, there were no galaxies, there was no source of light. It was just darkness. But as it got cooler and more expanded, eventually stars and galaxies started to form. And the way that we say it actually in astronomy is we talk about bubbles. So they started ionizing, which I will explain in one slide what I mean by that. But they started blowing up their own bubbles around them. And these bubbles started overlapping one with the other until we eventually got a universe that is full of light, which is what we see today. Now, my work is specifically trying to understand what happened there when these bubbles were overlapping. What kind of galaxies, what kind of stars, how did it happen? Yeah, it's an unsolved question. So this is the Epoch of Reionisation, and it's what I work on. So when I said ionizing, I mean hydrogen ionizing. You might be familiar, I think most people in the room have heard this in a physics course or something, ionizing energy, ionizing radiation. In astronomy, we tend to talk about hydrogen, and me specifically because it is the most abundant element on the universe. So we want to understand how that happened. So when I say ionizing energy, it just means that stars have enough energy that if you have a neutral hydrogen atom, so just a proton and an electron together, your light is energetic enough that it just breaks it apart, kicks out the electron, separates them. And every time that that happens, there is a possibility that they will meet up with another free electron, another free proton, and recombine and form hydrogen again. Every time that happens, it gives rise to a very specific signature in its spectrum. And I don't have access to spectrum because I work with NIRCam. So NIRCam is the imaging part. So I have pretty pictures, and I have to somehow figure out how a spectrum looks from that. The advantage of doing that is that you have much more galaxies and it's cheaper. The disadvantage is that you have to be very creative with how you go around it. So I'm specifically looking for these signatures. The way I do it, this is from one of my papers, not the cat, the image. So here we have one galaxy with different images in different bands, so it's different wavelengths. You can see there's a clear axis here in the middle compared to the others. And that is actually one of hydrogen's transitions. So the way that I do it, you ideally would have this kind of line that would be a spectrum, but I don't. I only have these squares that you see here. And as the galaxies get further and further away, this line would get stretched and redshifted more and more. So what I have to do is, with these kind of filters and these kind of observations, figure out how much flux is in that specific line. And from then start to make conclusions about what are the ionizing properties of galaxies. So there's lots of steps in between. If you're curious about the specifics, please feel free to ask me later. But one of the cool things that we did through this is about 700 galaxies, which was, again, I've said it a lot, but this was impossible before JWST to just have 700 galaxies, 2 billion years after the Big Bang. And what we did find is that here on the y-axis, I've modified them slightly from my paper so it's easier to read. So this is how efficient galaxies are producing this ionizing radiation that ionized the universe and made these ionized bubbles and gets us where we are today. And on the x-axis is just the time. So here we get closer to the Big Bang towards the right. And we do find a rising slope. It doesn't seem like much, but it does mean that galaxies early on in the universe were actually more efficient in producing this ionizing energy, and that might be why they ionized the universe at the time that they did it. The debate at this was always if it's galaxies or if it's supermassive black holes. And what we're finding so far is that it's galaxies. So galaxies might be small at that point, they might have low mass, but they seem to be enough to ionize the universe. So what drives this behavior? This is actually quite illustrative. It's the burstiness of how much they're forming stars, and that is driven by the mass of the galaxy. So if you have a low mass galaxy and you have stars being formed, eventually these stars will die. Some of them will be supernovae because they're massive, and they will explode. That will happen all the time in any galaxy that's producing stars. However, if the galaxy is low mass enough, then that will make a huge impact in the galaxy itself, because every time you have loads of supernovae going off, the gas will be heated around it. It will also be expelled a bit, and then star formation stops because you need gas to make stars. But then as time goes on a little bit, it will accrete gas just from outside of the galaxy, and it will start again. And this seems to be what's happening at the very early universe. So this was the most horrible GIF I could find, and I thought it was appropriate. So basically what my work is centering is understanding which galaxies and how they produce this ionizing radiation. But so far, we're finding that in the early universe, these low mass galaxies are enough. And they are enough because even though they're maybe small, they are quite dramatic. So their effects are important. What I'm doing right now, actually, though, is not published yet. This is top secret. Is that now I have... Sorry, I didn't notice the top hat. Now I don't have 700 galaxies. I'm actually looking at around 40,000 galaxies. So I think we're finally going to be solving once and for all that question. And then we'll just have to move, or I will have to move to new questions after that. So it's quite exciting. So these are my conclusions. So JWST has given us an amazing access to data that we never had before, and now you have access to it as well. If you're interested, I gave you the link. I can show it again if you want. I can't stress how amazing this is. This did not exist not even 5 years ago. This couldn't be done like this. Then we find, low mass faint galaxies are amazing. They like to produce ionizing radiation. They're very efficient. They're small but powerful, faint but dramatic. And then stay tuned for more JWST results coming up. And also, bonus, I have another QR code. So this is me with my own JWST. You can build your own if you want. It takes about a day, and it's loads of work, but it's really cute. So if you wanted to build your own JWST, that's it. And if not, I'll say thank you. I left time on purpose in case there are questions, so please, if there's any questions, I can try to answer them as best as I can. Yes?
So the Big Bang sort of assumes that everything started at one point. But then when you're looking back up to the CMB, sort of why can you see that all around you rather than just coming from one sort of point?
It's a good question. I'm not a cosmologist, but I think I know the answer to this one. The CMB comes from the inflation period, so that doesn't really, it doesn't tell us anything before that. I don't think we have any observations that can show us the Big Bang or if it was or it wasn't a point of that. But there's loads of physics theorists that work on that and have lots of explanations for it. Any other questions? Yes?
Why is the low mass galaxies more efficient?
Yeah, so I don't think I explained it very well, but it has to do with how bursty they are. That's why the fireworks. Hopefully this is a good memory aid. It's because every time they form stars, and eventually these stars supernovae and explode, they kind of deplete the galaxy from that gas, and they also heat around it, so new stars can't be formed immediately. So it stops the production for a bit. But then, since they're high redshift as well, there's gas all around the galaxies that gets falling into the galaxy, star formation starts again. When you have a massive galaxy, you still can have star formation going on and off. However, you won't notice the effects that much because it's so massive, it's got stars all over that have been forming for so long that you just don't get these effects. Yes?
On one of the slides in your PowerPoint, you had the spectrum that you said some scientists thought would be evidence of a black hole.
Yeah.
Would you be able to talk a bit more about how light spectrum could be evidence of a black hole?
Yes, of course. So black holes, as I'm sure you know, you can't really see the black hole because it eats all the light, right? Nothing comes out, no one can escape. However, supermassive black holes, if they are actively accreting matter, they're called AGN. So they're not just any black hole. They are black holes that things are falling into them quite often. And so since they're falling into them, there's a combination of angular momentum that just like when ice skater, spins and then spins quicker when they do this, as it gets closer to the event horizon, it goes faster and faster and faster until it falls into the black hole. This emits loads of radiation, loads of light, and that's what we see. So actually the regions that are closer to that event horizon where things are going really fast, you will see some effects happen. For example, this line that I said H alpha, this hydrogen line that just looks like a line, if it's happening very close to the black hole, it will start getting broadened because just the speeds do that effect. And also there's some thermal effects that also do that. So that's how we can kind of figure out if it's black holes or if it's just star formation. No worries. Yes, in the back?
You mentioned a little bit later on in your slideshow that the low mass stars, when they sort of die, they stop producing the ions.
To move my computer, like to move through this one,
Outside the galaxy,
is control or do I have to be next to
No,
No, sorry. That's not exactly what I said, but I think I said it in a confusing way. So it's not the low mass stars. It's just star formation in general in the galaxy that's turned on. So stars are being formed. And then the high mass stars, like above, I think it's like 8 solar masses or something, they die as supernovae. And these blow out gas. They also heat their surroundings. So that stops the star formation in the region for a bit. And then there's gas from outside of the galaxy or from different parts of the galaxy that falls in again. And then stars can be formed again just because you need cold molecular gas to form stars. So just this effect of supernova blowing it off and then it coming back again triggers star formation on and off in a galaxy. Yes?
You mentioned in the reionisation era, you mentioned bubbles. What were the bubbles? Was that a bubble of gas or just a
Yes.
area of space?
Sorry. So the bubble is that the universe was neutral, so it's just neutral hydrogen basically everywhere. But as these stars started to form, they produce ionizing radiation, so this just basically ionizes a region around them. And we call them bubbles because it's cute, but also we assume they're spherical, which they absolutely don't have to be, but it's just the best we can do, I think, at the moment. Yes, very much in the back.
So, using these bubbles and the James Webb Telescope, could you theoretically be able to determine if these theoretical quasi-stars would be able to exist within the early universe using these bubbles of ionization within these early galaxies?
Well, there's definitely people working on it. I don't know about those stars in particular, but have you heard of population 3 stars? So those, someone in my group actually, like my boss, has a paper on this GNZ11 that I showed. Close to this one, where they think they found signatures of this population 3 stars. These are just stars that were formed where there was no metal enrichment in the universe, so they're basically formed of just hydrogen, whereas all the stars we see now are formed by also heavier elements because everything just has heavier elements around it. So yeah, people definitely are doing that or trying to do that with James Webb right now. Yes?
Since sort of ionization usually sort of leads to more ionization, like in the sense that you need something which is ionized to create a ion. Like what in that universe of neutral hydrogen, what would sort of be the source of the first ionization?
The first stars, first galaxies. So it was neutral enough and cold enough that it could collapse under its own gravity, and then you ignite nuclear fusion eventually, and you get a star. And stars produce ionizing radiation. Yeah. Yes?
Do you think we'll ever have a satellite telescope which can see the white wavelength to see during the Big Bang what happened there?
I don't think so. I don't really understand enough, but we can't really see beyond. Like, there's a hard limit on what we can see, and it's the observable universe, just due to the expansion of the universe. I don't think we will ever see directly Big Bang, or, yeah. There's people looking for signatures of what could have happened before, but I think it's mostly theoretical.
Okay, Charlie, you want to take one more question?
Okay. So I want the final question. Yeah?
The rate of ionization changing as the universe ages, like it decreasing, and why?
So what happened is I didn't go into it, like with technical words, but after this epoch of reionization, the universe itself, so meaning we call it the IGM, which is the intergalactic medium. It's just the stuff that's between the galaxies. It's a fancy name for it. So that was neutral, and then after reionization, that is completely ionized, basically. So that's what we have today.